This is an introduction to the Monte Carlo simulation project. So in this screencast, I'm going to kind of give you an overview of what a Monte Carlo simulation is and why it is useful. So a Monte Carlo simulation is a simulation that takes into account the variability of the inputs. So you have a complex process, and if it's simple enough, you can just mathematically describe this. So what it does is it takes into account variation in your inputs. So maybe you have inputs A, B, C, and D. And maybe A is a randomly distributed variable. So it's a normally distributed variable. So it looks like a bell curve, which means that there's some sort of average or central tendency with a standard deviation. So there's a lot of things, a lot of variables that are normally distributed. But maybe B is something different. Maybe it's uniformly distributed. So maybe there's an equal probability of getting anything between little a and little b. So for example, this is if you have a six-sided dice, there's a 1/6 chance that you'll get a 1, 2, 3, 4, 5, or 6. So it's equally likely. So maybe your process has some input B that has a uniform distribution. You might have discrete variables. So maybe you have 1, 2, and 3 are the different possibilities, and each of those has its own probability. So maybe it looks something like this. So that's a discrete input. And you can also have variables that have some awkward shapes. So maybe like something like that, all right, where it's more likely to get something kind of on the right-hand side of this distribution. So all of these inputs, A, B, C, D, go into this process. And there's, this is normally described by some sort of mathematical process. You've got all sorts of relationships between the different variables, and the output then is really what you're interested in. A Monte Carlo simulation looks at combining the variability of all the inputs to get a distribution of the outputs. So you're not just simulating it once. You're not just choosing an A, a B, a C, and a D, but what you're doing is you're looking at maybe 1,000 to tens of thousands of different simulations. Each of those 1,000 to 10,000 simulations, you're going to randomly choose an A from its distribution, randomly choose a B from its distribution, and so on. So you're just going to kind of at random choose combinations of A, B, C, and D just by chance, by random chance. You're going to put those into your model process, and you're going to get the output. So you might get, for this example, you might get, some sort of probability distribution that looks like this. It's not necessarily just a simple Gaussian curve because some of the inputs are not normally distributed, like A. The output usually has some sort of probability function, all right, which is shown here. And you might be doing a financial project. You might be looking at modeling an investment. I'm not a business person, but maybe each of your inputs, A, B, C, D, has different probabilities or likelihoods, and then you put this together into some sort of process, and maybe this is the profitability of your venture, and maybe these ones over here, these are all profitable, and that's actually sort of what the project is going to entail. But maybe that's like 96% when you simulate it. 4% of the simulations is what this is telling you. 4% of the simulations, the Monte Carlo simulations, are giving a non-profit, so no profit over here. All right, so a Monte Carlo simulation, you look at the variability of all the inputs, you put it into your process. You do 1,000 to 10,000 different simulations. For each simulation, you're only choosing one value of each of the distributions. So maybe this is, by random chance, this is 4.2. This is 1.3. This is, you choose, maybe when you do a simulation, you get 2 is going to be your value because this is a discrete variable, 1, 2, or 3. And then maybe here you get a value of 147. And those all, depending upon what they are, they go into your process. And then you output for that single simulation, maybe you get one number, and maybe you're getting a profit of $10.1 thousand. All right, you do that 10,000 times, and then you take the results of each of the simulations. You take random inputs for each of the simulations, and you create the output. and then you plot that, and that's how you can determine, 96% of our simulations led to a profitable venture. So what is a probability density function? We're going to be using a lot of these probability density functions in this project. For discrete variables, this is also known as a probability mass function. The important thing is that this represents probability, and the area underneath the curve, if it's a discrete variable like here, the probability of all the bars always adds up to 1. So this is probability. The example I have here is you flip 2 coins. What's the probability that in those 2 coin flips you're going to get 0 heads? So that means this is also 2 tails. So that's just 1/2 for the first coin is going to be the probability of getting a tail, and 1/2 for the second. So it's 0.5 times 0.5 would be 0.25. So that's the probability that you'll get 2 tails, which is 0 heads. There's also a 50% probability that you'll get 1 head. So you can get head then tails, or you can get tails then heads. So there's 2 possibilities out of 4 possibilities total, and so this ends up being a 50% probability that you get exactly 1 head in 2 coin flips. And similarly, there's a 25% chance that you'll get 2 heads because you have a half chance in the first coin and a 1 in 2 chance in the second coin, so that's equal to 1 in 4. So a probability density function or a probability mass function, you'll also see this probability distribution function or just simply probability distribution. It just sort of explains or describes the probability of getting certain outcomes. Another example, this is a uniform distribution that I touched on a few minutes ago, is a dice. This is a uniform distribution because getting 1, 2, 3, 4, 5, or 6 is equally likely. So it's sort of just this flat distribution. For a continuous variable, where you can have a range of different values, not just discrete 1, 2, 3, and integer values, it looks something like this, where the area under this distribution is equal to 1. The normal distribution is the most common distribution. I'll talk more about this in individual screencasts on each distribution. But many objects, times of something, the costs, real-world phenomena are characterized by a normally distributed variable. The male height in a country, female height, so it's normally distributed. Maybe if you have sugar packets that you're putting in your coffee, if you weighed hundreds of those, you would see that they follow a normal distribution, all right, centered about some average. Manufactured parts, the dimensions, the weights of various manufactured parts are all oftentimes normally distributed. So the normal distribution, also known as the bell curve or the Gaussian distribution, so numbers kind of near the average are more common than in the tails. So if this average is equal to 5, it'd be unlikely but possible to get something way away from the average, and it'd be rare to get something like a 1 down here. The standard deviation means that what it really means is 68% of the distribution is plus or minus 1 standard deviation of the mean. So if I had a standard deviation which I represent as sigma equal to 2, then that would mean 68% of all possibilities described from this distribution would lie between 3 to 7. So that's 68% would be between 3 and 7. All right, and then it's unlikely to get something in the tails. All right, so in subsequent screencasts, I'm going to sort of explain an example. It's a Monte Carlo simulation of a cookie recipe and the cost of cookies and the profitability of cookies.